Hey everyone, it's Physics 40S, Dr. Carroll here. We are continuing on with potential energy, but now we're also bundling in kinetic energy. The total of kinetic and potential energy gives us what's called the total mechanical energy. So I'm going to use the mini text here on page 343. So I'm just going to write here that E total equals EK plus EG. Now you can complicate it a bit and talk about spring potential energy, and we'll get to that in a minute, and conservation of energy in general, which is that energy is neither created nor destroyed, but rather is transformed from one form to another. But if we have a specific case of just looking at gravitational potential energy and kinetic energy, we can talk about the total. Just as a reminder, you see at the top of this page, I still have assignment Z textbook questions listed. So to make sure you get those in. The dates will be posted on Edsby. So how does this total kinetic energy work? Total mechanical energy. Remember, kinetic energy is 1/2 mv squared, and the relative potential energy is mgh. So E total will always be the sum of 1/2 mv squared plus mgh. And a classic example that we look at is a roller coaster. Now these roller coaster questions, some like them, some don't. I guess you could say they have their ups and downs. I will tell that joke every day. I teach this for 28 years. So here we have a roller coaster. It's on the bottom of page 343 and then on to page 344. So we see different points, and where's my arrow here? Okay, so we have here point A. There we know what the speed is, 10 meters per second, and the mass of the roller coaster is 1,000 kilograms. So I can get the kinetic energy at that point. It'll be just 1/2 times 1,000 times 10 squared, which is 50,000 joules. So that's my kinetic energy at A. I can also get my potential energy at A. It would be mgh. 1,000 times 9.8 times 6, which is around 58,800. So add those together, your total mechanical energy is 108,800 joules. And that is the same mechanical energy everywhere. It's the same as B, where we're going to have a little more kinetic energy, a little less potential, because we're getting closer to zero. Then at C, we are at our 0 point. I really don't want to say ground level, because you don't want to make a roller coaster at ground level. So this could still be up on scaffolding. If it's on ground level and you walk by with your root beer and mini donuts, you might be in for a rude surprise. So there's a scaffolding, but you take your reference frame to be the 0. That's the key. And at point C, there is no more potential energy relative to your reference frame. All of the energy of the roller coaster cart is in kinetic. And the total is still 108,800. Then at D, well, that's going to have the same kinetic energy and the same potential energy as at B. And the total is going to be 108,800 joules for this case. And then you go on and you look at point E. So we can tabulate this data. And this is always a good idea in these conservation of energy questions, because mechanical energy has to be conserved. Well, if it has to be conserved, then your energy always has to be the same. So here we see the different values, time interval A. You can get the speeds at all these once you get the kinetic energy. Remember, the total mechanical energy always has to be the same. Not always 108,800, but for this question, yes, 108,800. And so you see that at the bottom of the roller coaster, it is the greatest speed, 14.75 meters per second. So what does it say here? As the coaster falls, the decrease of gravitational potential energy is compensated by an increase in kinetic energy, so the coaster picks up speed. Once the conditions of velocity and height are known, the total mechanical energy can be calculated, and the total mechanical energy can then be used to evaluate the gravitational potential energy at any point along the trip. So that's exactly what you do. And let's try this example. what is the kinetic energy when the roller coaster has an EG of 19,600? So, was that in the table? No. So that's at some other point. And so, if the gravitational potential energy is 19,600, as we see here, and we know that the total mechanical energy is 108,800, then the kinetic is going to be the total minus the gravitational potential. So 108,800 minus 19,600, which is 89,200 joules. So that's the kinetic energy. Part B asks, how high is the roller coaster? Well, I know the gravitational potential energy, so EG equals mgh, right? EG equals mgh. So the height is EG over mg, 19,600 divided by the product of 1,000 and 9.8. So it's at 2 meters, which wasn't one of the points tabulated. It's between there. But it all makes sense. And so our speed is going to be somewhere between, if you're 3 meters above the reference point and 0. So the speed is the square root of 2 ek over m, and you get 13.35 meters per second. So that's an example of a roller coaster problem, and they won't get fancier than that. I think I might throw a loop-the-loop in on one of them. Not much more fancy than that. So let's go to example 14. Here we have a boy, and not just any kind of boy. The textbook says an inquisitive boy. Okay, so someone wants to know about mechanical energy, throws a stone towards the ground from the top of the roof, which is 3.2 meters high. So let's make the roof like a flat roof to make it easier to do the question. And so this isn't a stone being dropped, it's a stone being thrown. So we throw the stone down. The mass is 0.5 kilograms. The initial speed, VI, is 1 meters per second. And H is 3.2 meters. What's the gravitational potential energy and kinetic energy at the top, at the beginning? What's the total mechanical energy at the beginning, at the end? And what speed will the stone hit the ground? So rather than reinventing the wheel, it's all typed better for you, so I'll just go straight to the explanation. The gravitational potential energy, mgh, at the top of the roof. So 0.5 times 9.8 times 3.2 is 15.68 joules. And the book, because it has nothing more exciting that it likes to do, plays with the sig fig, so it rounds it to 16 joules. Fine. The kinetic energy is not 0 because, again, you aren't dropping the stone, you're throwing it. So it's 1/2 mv squared. So 1/2 times 0.5 times 1 squared is 0.25. So if I add those two values together, again, why did they round off here? Let's change that. Let's put 15.68, right? Okay, so total mechanical energy at the top is 15.68 plus 0.25, so 15.93 joules. And it's a closed system, so the total mechanical energy of the stone should remain the same throughout the trip. And if there's air resistance and friction, then it's different, but that's for next course when you talk about air resistance. So mechanical energy remains the same throughout. Just before it hits the ground, all of that energy is kinetic. So the mechanical energy, the 15.9 3 joules, I'm going to put that here, 15.93 joules times 2 divided by 0.5, 8 meters per second. So the speed of the stone as it reaches the ground level is 8 meters per second. Okay, so that was all shown on page 345 in the mini text. Okay, let's try one more here. I don't know if we do archery at the school. My guess is probably not, and certainly not in the gym. But that's what example 15 is about. I guess you want to get the point about this one. A high school student, that could be you, shoots an arrow straight up in the air at 30 meters per second. Assuming no air resistance, what's the maximum height that the arrow could reach? And how fast is the arrow going when it hits the ceiling at a height of 15 meters? And again, we're going to assume that the arrow is launched right from the ground. Okay, so maybe the person's lying on the ground and using a crossbow system. So we know the mass is 0.04 kilograms, and we know the speed initially is 30 meters per second. And it's going to slow down as it ascends because of gravity. So at the ground level, the gravitational potential energy is 0. We're going to make that our reference point. And the question, part A, says, what's the maximum height? So all of that initial kinetic energy, because you're launching it at 30 meters per second, is going to be converted into potential energy. At ground level, the total mechanical energy is expressed as kinetic. So 0 joules gravitational, 1/2 mv squared for the kinetic. So 1/2 times 0.04 times 30 squared. So now you know that the mechanical energy in total is 18 joules. Capital T stands for total, not for period, not for temperature, but for total. If you'd rather write out the word total each time, or TOT, go ahead. Set. It's always a good idea, as soon as possible, get the total mechanical energy, because that can be used in more than one part in the question. So, at maximum height, speed is 0, but the total mechanical energy stays at 18 joules. So your 18 joules equals the gravitational potential energy. So H is going to be E total over mg. So 18 divided by 0.04 times 9.8. So the arrow could reach 46 meters. Now, you'd want to have a hole in the roof of the gym first, because there's no gyms in high schools in Canada which are going to have ceilings of 46 meters, at least none that I know of. The second example is, what about at the 15 meter mark? So there are some gyms which are at least 15 meters. So remember, the mechanical energy in total is still 18 joules. So at the 15 meter mark, you're going to have non-zero contributions from both the gravitational potential energy and the kinetic energy. So the gravitational potential energy is 0.04 times 9.8 times 15, that's mgh, plus 1/2 times 0.04 times v squared. So isolate for v, 18 minus 5.88 divided by 0.02, take the square root, and the arrow is going at 24 meters per second. What did it start at? 30 meters per second. And at 15 meters up, it's at 24 meters per second. At 46 meters up, it's at 0 meters per second. Okay? So let's see what the next one is. Conservation of mechanical energy. Here are just some interesting pictures of pole vaulters, and no, these are high jumpers, not pole vaulters. Then there's flow charts, which I'm never really interested in. And then we have a case for you to practice on your own and applying the concepts. You can try question 1 on your own. Okay. Now that's actually it for the mini textbook. The answers again are at the back of it. And so now I want to bundle in a discussion about the spring bumper. But I'm going to pause for a second so I can get to that, switch to the our booklet. Okay, so it was the first time I tried that pause function. I hope it worked. I'll find out in a few minutes. So I'm on page 5 in our booklet. I'm not using the mini text anymore, so you can don't need that for the rest of this lecture. And just remind you, law of conservation of energy. Energy is transferred from one form to another It's not lost or created. Total mechanical energy, we looked at that. But sometimes there's other kinds of energies that show themselves in the conservation of energy idea. And one is a spring bumper example. And let's just focus on the horizontal spring bumper example. So what you have, and you have these in your cars, you have bumpers with little springs on them, and they're supposed to help in case if there's fender benders on the icy roads that we all know we have almost every day in Winnipeg. So here I have a before picture. So I have some wall, let's say, I have a spring, and then I have some mass attached to it, and it's on essentially a frictionless surface, and I have it spring loaded, like maybe a paintball spring, pen spring, and it was 6 centimeters pushed in. Then I release the blocking that kept the mass in place, so the mass will move to the right, and as it does, it picks up speed, it picks up kinetic energy, because now the stored elastic potential energy is being converted into kinetic. So we want to find out, once you're back at equilibrium, how fast is your block of wood moving. You're given the spring constant, 50 newtons per meter, you're given the mass. So initially, I'm going to just rewrite this here. So 1/2 times the mass V initial squared plus 1/2 K first position squared is 1/2 M V final squared minus 1/2, or the plus, not minus, plus 1/2 K X final squared. So we had this loaded into position, so it wasn't moving originally. So that's 0. And we're going to have the final X is going to be 0 because we want to get back to equilibrium. So that's 0. So I can isolate for VF. The halves go away. So just the square root, and you see it right here, Kx initial squared over M. So in cases where I ask for the maximum speed, because that's when the maximum speed will be, it's not going to get faster past that. Some kids say, oh, well, if you extend it even more, it's going to get faster. No, if you go past equilibrium, then the spring is going to be restoring you back to equilibrium. In fact, and we'll look at this just a tiny bit, but what we're looking at is simple harmonic motion. The block isolating, not isolating, we've been talking too much about that. The block oscillating back and forth between the equilibrium position. So VF is the square root of K, so that's 0.06 squared times 50. KXI squared. I have, yeah, I put the 50 after, so fine, right, fine, that's okay. Divided by the mass, so 50 is my K, 0.06 is my X, square it, divide by 5, take the square root, and you're going at 0.19 meters per second. So that is a classic spring bumper example. Let's look at another one here. In this one, we still have the same spring, but we aren't going all the way to equilibrium. So in the second one here, I have before and after. So I want to get the speed after, so that's the 1/2 M. I can write V final squared. But isolating for the K, it's going to be 1/2 K XI squared minus XF squared. This is not correct. I'm going to cross that out. That's not correct. Let's cross this out and let's do it right. So here you go. 1/2 times K times xi squared minus 1/2 k times xf squared. I don't know why that came. Get rid of that silly thing. Equals 1/2 mv final squared. So the 1/2s go away. That's great. So I get k, which is 50, times 0.08 squared minus 0.05 squared. 0.08 squared minus 0.05 squared divided by m, which was what? It's the mass, 5. Take the square root, and I get v final. So 50 divided by 5 is 10. So I got point, and I got that in the wrong place too, don't I? The squared should be here. So 0.08 squared minus 0.05 squared times 50 divided by 5. Take the square root. 0.20 meters per second. So yeah, so that answer was wrong at the back of the book here. In fact, to even make it simpler for you, I'm not going to ask this question at all. I'm going to ask the one where you get the maximum speed. But just if you ever came across it, there it is for you. Now I'm going to no, one like that, we already did that one. So I'm going to jump to a concept that is not, no, it's actually on page 10. So I'm going to jump to page 10 to talk about the period of the block in the spring bumper. So I'm going to scroll down and watch this. This is gonna get your bearings all mixed up here. Watch this. Rotate, 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 rotate. There you go. Page 10. Mass on a spring. I can get the period on that mass on the spring if I release it. And so we have here that the period is 2 pi root m over k. So again, if it oscillates back and forth. So here we have a mass on a horizontal spring bumper. It's at equilibrium. Then I push it in, take it out, and that's all good. This part here, I'm not going to bother with that in this at this time. So, but I do want to look at this equation here. So let's say you had a mass of 4 kilograms and a k of 3 newtons per meter for my force constant. Then I want to get the period here. So all you do is it's 2 pi square root of m over k. And you can prove that on your own if you're really interested. And the units do work, right? We want the units of period to be seconds. So it's just 2 pi square root of 4 over 3, and you get 7.26 seconds. So the more massive the block is for the same spring, the higher will be the period, right? The longer it'll take to do that full motion. What's a full motion? If I start at equilibrium, push in, go back to equilibrium, extend, and then go back to equilibrium again. So there's like 5 steps, right? Equilibrium, in, back to equilibrium, out, back to equilibrium. Known as simple harmonic motion. Let me write that word there. Simple harmonic motion. Okay, so that is the mass of the spring. And again, I'm going to leave off that part there. And the final topic, I'm going to leave that for our next lecture, is how pendula work. Pendulum. One pendulum, two pendula. So I'll leave that for the next class. And so today we looked at mechanical energy and roller coasters, archery, throwing rocks, and we looked at the simple harmonic motion case of a spring bumper and the relationship between spring potential energy and kinetic energy. Hope you enjoyed it. There are some videos about this. If you just go to our website, there's videos you can watch that I curated especially for you. Enjoy.